summary of system modeling. So these are the different things we're talking about. It's all about modeling, different aspects and different types of modeling. So system modeling is, as it says, the process of developing abstract models of a system so that you can have different views on the system. We're going to be using UML, the Unified Modeling Language, to do this. And the aim is to understand more deeply what the connections between the different parts of the system being designed are, right? Because we need to understand that, because we may find things about the design, but the main reason we're doing it up front is to find more things about the requirements. As it says, they help clarify what the existing system does, which may help find strengths and weaknesses, it's to help explain to the stakeholders the requirements. Model-driven engineering across all sorts of engineering is very useful because it's more of a paper study, and paper studies can be done much more quickly and much more cost effectively before we decide to actually build whatever it is we're trying to build. So system modeling is very important. Right? So there's various perspectives of the system. There's the external perspective. There's an interaction perspective, how the system works between itself and the environment. There's a structural perspective. What's the organization of the system? And then there's a behavioral perspective, which is how does the system change over time? What's its behavior over time? The sorts of diagrams we're going to use are activity diagrams, use case diagrams, sequence diagrams, class diagrams, and state diagrams. We've already done quite a bit on use case diagrams, and we've started to look at sequence and class diagrams. We still need to cover in class what activity and state diagrams are doing. And the aim with these is you can use UML to be very pedantic and very specific, but for me the biggest benefit of UML is to be able to draw something for somebody else to discuss software, rather than having to code something up to discuss software. And that's the biggest benefit. You can use a case tool, the computer-aided software engineering tool, to be able to build software from UML, but a lot of places don't do that, and it's arguable what the benefit is, depending on the context of the software. It's a useful way of documenting the system. A lot of tools, I believe Eclipse and I believe Visual Studio, allows a level of auto-generation of UML diagrams from the code, which is a nice way of being able to overview the code and see the connections between the code without having to read through lots of code. So context models, they're used to illustrate what the system is doing in context, where it's going to be used. You can deal with social or organizational concerns, and architectural models show how the system sits within potentially complicated IT infrastructure. These days, the IT infrastructure you're likely to meet is a cloud-based system for some parts, a mobile application, a mobile-based system for other parts, and potentially the IT infrastructure between those two. That's why it's very important to determine the system boundary, right? And to some extent, as it says in the third bullet point here, defining the system boundary is a political judgment. You may have to work with people in order to define which parts of the system you're designing you have control over. It may be you don't have control over some parts of the system, even though you're going to be interacting with it. And here's a look at the systems involved in the MentCare case study. There's external systems to MentCare. There's the patient record system, the admission system, the prescription system, appointments, HC statistics, and management reporting. All of which are systems that the thing we're building, in this case MentCare, are going to use or access. So context models only show the environment. They don't show how it's used. So you need process models, and in particular UML activity diagrams, in order to show that. And here's another example. An activity diagram is another name for a flowchart. You've all probably thought about flowcharts. Activity diagram is just a bit more of a what's the word, specified, or a bit more pedantic look at a flowchart. So the flowchart starts with the fixed blue dot in the top left, and it ends with the white annulus blue dot on the right hand side. Okay, so there's lots of various steps. You can see there are guard conditions, right? Not available, available, dangerous, not dangerous. There are parallel paths through the system, right? You can do these things at the same time. You can do these three things at the same time. There's only one path from here to here, but there's three possible ways, but it only happens in one of those three possible ways. Interaction models, right? You want to know how the user's going to use the system. You want to know how systems talk to each other. You want to know how components within a system talk to each other. And use case diagrams and sequence diagrams are the way we do that. We've already talked about use cases, so I'm not going to delve too much into that. You need to have usually the use case diagram as well as the use case report. Right, there's a use case diagram. In this case, the use case association between medical receptionist and transferred data is directed. And that's because, well, I'm not quite sure why it's because I would expect in most associations you need two-way communication, as I think I've commented before. Here's an example of the Sommerville template for a use case. It's a little different from the one we've been using, but not especially. It's got similar fields. You should have mostly the same information as the template we've been using. Right, and here's a more complex one that just involves the medical receptionist and the functions that they need to perform. The thing that use case diagrams don't do is that they don't show step by step how things happen. The use case reports will do that. The basic or the happy flow will do that, but the UML diagram that shows that is the sequence diagram. And here's a sequence diagram. Right? We've got the medical receptionist on the left-hand side, and I think I mentioned that these black dotted lines are the timeline. Time is increasing as we go down the diagram. These blue lines, these thick blue boxes, they're called lifetimes. Right? So the medical receptionist exists for the whole of this sequence diagram, but the authorization only needs to exist for a short period in order to get the authorization to access the system. And then here we've got a guard condition. Only one of these things happens. If the authorization is okay, we get the patient info. If the authorization fails for whatever reason, then we get an error. And here's another one with another system which looks like it's helping us log in, similar to the way that when you log in to most things for Fairfield University, you get directed to the single sign-on page before being redirected to whichever aspect of the IT system within Fairfield that you're using. Sequence diagrams, as I said, talk about interactions and time-based things. Use case diagrams don't. The other thing that we need to start doing with our thinking about software is structural models, right? It starts to set the organization of the components of the system. They can be static or they can be dynamic, depending on the context of what the model is trying to achieve. We've already looked a little bit at class diagrams, and this is now starting to sound like software, right? Class diagrams show the name of the class, potentially the stereotype of the class, the information or the data contained in the class, the fields of the class, their types, their protection levels, and also the methods and their protection levels on the class. Right? And here's where you might start. You don't know too much about it yet. We know we have a patient class and we have a patient record class. And here's a lot of others. And remember, I talked about the numbers, 1 ... star or 1 or whatever on each of these associations. That's talking about the multiplicity of the class nearest the range, right? So down the bottom here, for some reason, they've decided that there are a consultation is only run by up to 4 doctors. You can't have an unknown number of doctors involved in a consultation. And here's an example of how you might write the consultation class. Consultation class has doctors, date, time, clinic, reason, medication prescribed, treatment prescribed, voice notes, etc. And then the methods are new, prescribe, record notes, transcribe, etc. A very important relationship when we talk about object-oriented programming or object-oriented analysis and design is generalization or inheritance, right? So rather than go into excruciating detail in lots of different things, some parts of those lots of different things are in common. So we try and generalize from all of the entity classes that we've got into something, a subset of their fields and methods that are generalizable. right? And I'm not going to read through this. You can read through the slides as well as I can. But the idea here is that we use this sort of arrow, this open arrow, or rather unfilled in arrow, where we have the general class is the doctor, but we can be more specific in that the general practitioner is a type of doctor, the hospital doctor is a type of doctor, the consultant is a type of hospital doctor who's a type of doctor, the team doctor is a type of hospital doctor, the trainee doctor is a team doctor, is a hospital doctor, is a doctor. The qualified doctor is a type of team doctor, which is a type of hospital doctor, which is a type of doctor. Okay, that's inheritance. And usually what you do with inheritance is you add some extra information, right? In the case of a hospital doctor, they are internal and you might have a staff number and a pager number. For a general practitioner or a primary care physician, they may not be internal to our hospital or our health facility, so you need to know the name of their practice and the address of their practice. So this is an aggregation model, and the idea is that it shows how the different classes are connected to each other. And in this case, aggregation is using the open diamond for the connections, and you can see the multiplicities are also labeled. So behavioral models. These are showing what the dynamic behavior of the system. And there's two things that you need to think about that impact the dynamic behavior of your system. There's the data and the events. So a lot of systems are data driven. You get some data in, you process it, you update other data. So understanding what the inputs and outputs and processing are happening is very, very relevant. Right? So here's an example from the insulin pump case study showing how things move from the blood sugar sensor to getting the sensor value, to getting the data, to computing the blood sugar level, to figuring out how much insulin you need, to telling the pump how to deliver that insulin, and then finally delivering the insulin. And here's another sequence diagram example which shows how we do order processing. And so that first one was about data driven, and now we're more event driven. Mobile applications are often more event driven because you've got people tapping on the screen, you've got notifications arriving. Those things are events, and they're got to be acted on. So state machines are often useful for that. And here's a state diagram, and the top of each of these shapes is the name of the state, right? And we start here, and we can only transition to another state along the arrows. And this is saying we go to full power, we want to set the timer, we set the numbers, the door closes, we can start, the door opens, we disable it, we start again. Once the oven is finished operating or gets cancelled, we wait and then we finish. And again, we're starting at this filled in blue circle and we're finishing at this blue circle with a white annulus around it. You can do things you can nest state diagram. This is a state chart. You can nest state charts so that one big state, the operation, may have lots of things happening inside it. And these are substates of the operation state. Right, and this is usually you go with a diagram and then a description of each state and a description of each of the transitions for each state. As I said, one thing we're really interested in doing is being cost effective in the way we do engineering. And model-driven engineering in every part of engineering that I know about is the way to do that cost effectiveness. Right, and one nice thing about model-driven engineering in software is that you can use hardware or software platform to auto-generate parts of the things that you need. And the one nice thing about model-driven engineering is that it raises the level of abstraction with which you think about the problem and with which you think about solving the problem, and that's very useful. Right? Some of the cons, sometimes the models that you use for abstraction are not great for implementation. And sometimes the savings from generating code may be outweighed by the costs of developing translators for new platforms. So it depends on the system. This is the computer-aided software engineering tools that I'm thinking about. And you can develop a model at different levels, right? There's a computation independent model, there's a platform independent model, and there's platform specific models. And here's a way you may have to move from your original system, your computation independent model, with some domain-specific guidelines to get a platform-independent model. You add to the platform-independent model, you add some specific patterns and rules for a platform, which gets you the platform-specific model. And then you add once you've chosen the language, you add language-specific patterns to get executable code. Right, and here's an example of the sort of thing you may want to do. You may start off with a platform independent model that's got to be written in, eventually run in both Java and C#. So this is the way you might achieve that. I'm not convinced by what's happening on this slide. I do think there is a tension between agile and documentation, or agile and architecture, but I don't think that necessarily means that you can you abandon using a level of model-driven architecture. It does help to have a good tool. The tools I've used for model-driven architecture are Rational Rows and Rhapsody. Rational Rows I used for a C++ project or series of projects, and Rhapsody I used for an embedded C project, and C++, but it was an embedded project. one of the things with, if you're developing a system that's got a long lifetime, you may want to think about who's supporting the model-driven architecture software, the tools that you're using. So you may want to work with a product from a larger company. I believe Rational Rose is now run by IBM, so I don't know whether you can get much larger in software than IBM. That's just reiterating the models are good for facilitating discussion, but maybe the abstractions aren't necessarily the right things for implementation. The thing is, for most complex systems, the biggest problem is the requirements. The implementation is not generally the problem. The problem is getting the requirements right, and that's what the model-driven architecture is aimed at doing. And as it says, there's only certain cases where platform independence is really worthwhile. The one I think I told you in class, the one I worked on, the Rhapsody one, we deployed that system on a DVR, on a Fire panel, and I've forgotten the other one. There was another one. Oh, and an access control system. So that was pretty good. Okay, wrapping up. A model is an abstract view of the system. It lets us think about the system without developing it. The context model shows how it's going to be used. Use case and sequence diagrams describe the interaction between the system and its users. Structural models show how we're going to organize the system. Behavioral models describe the dynamic behavior. Activity diagrams can be used to model processing of data, and state diagrams to model the system's behavior. And then finally, model-driven engineering is an approach to software development which often helps for deploying the same system to multiple platforms. Can be very useful for that in that regard.